Let's now think about the energy stored in an oscillator, a mechanical oscillator. The energy is stored in two forms. There's a kinetic energy of the mass and the potential energy stored in the spring. So let's think about the kinetic energy first. So kinetic energy is very simply given by half mv squared, written v as the derivative of x here. And we can substitute in our solution for x, a cos omega t plus phi, and take its derivative, and then we can write half mv squared as a half ma squared omega squared sine squared omega t plus phi. So this here, this is the kinetic energy of our mass. We can also write this as half ka squared sine squared omega t plus phi, taking the omega squared and replacing it by k divided by a. And so you have some cancellation that goes on here, and so we can eliminate the omega and the mass and replace it with the spring constant if we wish. Next, we move on to the potential energy. So the potential energy in the spring is given by a half kx squared. And so substituting in for x, the position, we get a half ka squared cos squared omega t plus phi. What's the total energy in the oscillator then? Well, we add these two up. Sum of the kinetic and potential energy is a half k squared a squared cos squared blah 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 blah. But here we have a cos squared plus a sine squared, so we can, with the same argument, so this part here inside these brackets settle equals 1, so we can get rid of it, leaving us with an expression for the total energy as half k a squared or half m a squared omega squared, and that's just rearranging the k to be equal to m omega squared here. So these are two different ways of expressing the total energy in an oscillator. Okay, so in this case we've assumed that the energy in the oscillation is constant, that is, there is no loss of energy during the motion of the oscillation. This is a fairly unphysical situation. In every conceivable physical oscillator, energy will be lost to friction, and therefore there'll be some generation of heat. The kinetic energy is converted into heat typically. So we're going to think now about an oscillator with some loss, and we're going to imagine that as the mass is now being dragged along our frictionless surface, but our frictionless surface has some fluid in it, and we have what we call viscous damping in this fluid, and this, as you're pushing the fluid around, adds a damping force to the motion of the mass. So as before, the restoring force due to the spring is given by Hooke's law, so force is equal to negative k times x, but now we're going to add this damping force. This damping force F is given by some constant R, so it depends on how viscous your fluid is, how much resistance there is into the motion, but the force is proportional to the negative of the velocity of the mass. So the faster the mass is going, the higher the damping force will be, and the damping force is always in the opposite direction to the motion of the mass, so it's in the opposite direction to the velocity. So whichever way you're going, the damping force is pushing against you. Now from Newton's law, we have that sum of the forces must be equal to mass times acceleration, so we add up the Hooke's law force from the spring and the damping force from our viscous damping situation, and we can write down a new equation of motion where the acceleration, x double dot, is given by some term proportional to the velocity of the motion and the position of the motion. So this term here is what we had initially. This is the new term here, which is due to the damping. And we're going to look for a solution to this equation now. So the solution to that equation will look something like this. It's going to be some sort of a decaying exponential, which is now multiplying our cosine or sine function. So the amplitude out the front here that used to be a constant is now decaying, but we still have this thing which is oscillating as a cosine with a phase shift, or equivalently as the real part of a complex exponential, or equivalently as a sum of complex exponentials. The rate of decay here, gamma on 2, gamma is given by r on m, and the oscillation frequency here is now given by this equation here. So you can see this oscillation frequency omega with damping is just a little bit slower than the oscillation frequency without damping, which is omega naught. The solution here, which includes an oscillation, is valid provided gamma on 2 is less than omega naught. If the damping here is too big, so if gamma on 2 is greater or equal to omega on naught, then the system is so damped it stops oscillating altogether. So you can imagine that, instead of having water or oil here that you're dragging your mass through, you use something like honey, the mass will just kind of go bleh and won't oscillate at all. So we're thinking about a regime here where the damping is small. This damping rate here is small compared to the natural oscillation frequency omega naught. In fact, it's also worth noting at this point that if the damping here is sufficiently small, like a factor of 10 or so less than omega naught, then it's valid to approximate omega as being equal to omega naught. That's a really good approximation, and it's an approximation we often make. Let's now look at an example of some data you might measure if you were to do an experiment where you're monitoring the evolution of a damped oscillator. So on the y-axis here we have the position of the oscillator, or the voltage, or whatever parameter is oscillating. We can assume it's position for simplicity. On the x-axis we have time. Now the equation that fits this data is given by our solution to the damped oscillator here. So we have parameter A naught, some damping rate gamma, frequency omega, and a phase phi. How are we going to find all these parameters? Well, we need some information first. We need some starting conditions, so we need an initial position. The position initially at time equal to 0, we can just read off the graph because we've got a graph of position. So for our case, at time equal to 0, we have an initial amplitude of 2. Velocity is not so straightforward, it's not shown on this graph. We're going to assume it's 0, which is the way I've plotted this data. But if you're doing an experiment, you'd actually need to determine the initial velocity to do this properly. Now, to start with, we're going to read off the damping rate gamma and the frequency omega. I'm going to read those off from the graph. To start with the damping rate gamma, we're going to look for the time at which this exponential envelope here, which is this red curve, we look for the point at which this envelope has dropped by a factor of e, and that will correspond to the time at which this exponent here, gamma on 2 times time, is equal to 1. So the time at which this is dropped by a factor of e will correspond to the time equal to 2 divided by gamma, giving you this exponent of 1. So let's look for the point at which this thing is decayed by a factor of 1 on e. We're starting with an amplitude of 2, so 2 divided by e is about 0.74. We go over here to the time at which that has decayed by that amount and find that is equal to 10 seconds. So 10 seconds must be equal to 2 divided by gamma, giving us a gamma of about 1 divided by 5 seconds to the minus 1. For the frequency omega, we can just count 10 oscillations. 10 oscillations occur in 6.7 seconds, giving us a period of 0.67 seconds and an angular frequency of 3 pi seconds to the minus 1. So now we have the frequency omega and the damping rate gamma. We just need A naught and phi. I'll note at this point as well that we are in a regime where gamma is much, much less than omega. And I'll say something about that a bit later on. Okay, so we're back to finding A naught and phi. We note here that if phi happened to be equal to 0, life would be pretty simple, because then at time equal to 0, this cosine function is equal to 1, which means then this A naught must be equal to our starting amplitude of 2. But we can't be sure that's the case, so let's do some rigorous maths first. We'll substitute in our initial conditions, so at time equal to 0, we have initial position of 0, which gives us A naught times cosine phi is equal to 2. To do the initial velocity, we take the time derivative of our function here and then evaluate it at time equal to 0 and set that equal to our initial velocity. So if we take the time derivative of this and set time equal to 0, we would find this equation here, and we set that equal to 0. Solving this for phi, we find that tan phi is equal to gamma on 2 omega, which is equal to 0.01. So in fact, phi is very small. It's approximately equal to 0 because gamma is much, much less than omega in our case. So that's cool. For small damping, in this case, we get phi roughly equal to 0. But this won't always be the case. It's not a general result that for small damping phi is equal to 0. It just happens to be the case where we have a small damping and an initial 0 velocity. What we can say in general, however, is that for small damping, phi is decoupled from gamma. And what I mean by that is that if the damping rate is small enough, we can sort of ignore this term here, and then the phase of the oscillation is not affected by the fact that the system is decaying. So if you measured the phase of this oscillation by fitting an undamped sinusoid to it by sort of lining up the peaks, that would give you the phase phi, and then once you know the phase phi, you can calculate the amplitude A0. That's a bit of a detail, we don't need to worry about it too much. Okay, net result then, however, is that in our case here, we have A0 is roughly 2, using this approximation here, and so finally we reach the conclusion that our damped system here is well modelled by this equation here.